Welcome back to the next lecture in this climate change subject. And last lecture we talked about how the sunlight from the sun and the angle of the Earth's axis, or the rotation axis, affects the seasonal cycles as the Earth moves around the sun every year. And now what we're going to talk about in this lecture is the way that changes in the Earth's orbit around the sun affect long-term climate variations. And these long-term variations in the Earth's orbit around the sun affect the amount of sunlight that the Earth receives on very long timescales and lead to cycles of about 100,000 years in length between glacial periods, or ice ages as they're often called, and intervening warm periods, or interglacial periods. And we're going to look at how those effects are caused by changes in the Earth's orbit around the sun, and those cycles are called Milankovic cycles. So we're going to look at those in this lecture. So first of all, there are three different ways that the Earth's orbit around the sun is changed. And these are just natural periodic variations. I mean, as the Earth rotates and orbits around the sun, it wobbles a little bit like a top. And the first thing that changes is what's called the eccentricity of the Earth's orbit, and that's how elliptical the orbit is. And you can see here that in this part of the Earth's orbit, the Earth would be a little bit closer to the sun, and then in this part here, the Earth is a little bit further away from the sun. That's called the eccentricity of the Earth's orbit, and it varies over time. We also have a small variation in the Earth's tilt, or the axis of rotation wobbles around a little bit, slightly changing the tilt, and that's called the obliquity. And then we have a final variation called the precession of the Earth's orbit, and that's the date or time in the year, in the calendar year, at which the Earth is closest to the sun or furthest away, and that varies as well. And that then changes the amount of sunlight that would be received either in the northern hemisphere summer or in the southern hemisphere summer. And each of these variations have slightly different periods. And the first thing we're going to look at is the change in the eccentricity, varying between a more circular orbit and a more elliptical orbit. And that change leads to about a 6% variation in the intensity of the sunlight between the closest point, and the closest point is called perihelion, and the furthest point in the Earth's orbit, aphelion. But it turns out that as we go round, the Earth goes round in its orbit, this doesn't lead to any change at all in the annual average amount of sunlight that's received at the top of the Earth's atmosphere, averaged over the whole surface of the Earth. So there's no change in the total annual amount of sunlight received by the Earth, but there's a difference between the sunlight received, or the intensity of the sunlight, at the closest point and at the furthest point. And that leads to about a 6% variation. So we can see these variations. We can see that the change in the eccentricity has a periodicity that occurs, and here's the time scale down here. That change in the eccentricity occurs with a period of about 100,000 years. The second variation, the change in the orbital tilt, or the axis of rotation, happens at about a 41,000 year period. And the final one, the precession of the Earth's orbit, that's the most rapid, but it still only happens not quite as regularly. It wobbles a bit with about a 10 to 20,000 year periodicity. So now let's look at the changes in the axial tilt, or the obliquity, and this is really the angle of the Earth's axis. The more tilted is the Earth's axis will be the larger difference between the amount of sunlight received in summer and the amount of sunlight received in winter. The bigger the tilt, the bigger the seasonal variations. And it doesn't vary very much. Currently this tilt is minimum at around 23 degrees, and it goes up to about 25 24.5 degrees. Currently the tilt is 23 degrees. Minimum is 22, maximum about 24.5 degrees. And as I said before, varies with a period of around 41,000 years. And now the precession of the Earth's axis, or the precession of the Earth's orbit around the Sun, changes. Period typically of around 26,000 years, but there are also shorter period variations, as you can see in this graph, and this will affect the date at which the Earth is closest to the Sun, or the date of perihelion, and currently that's in January, which means that the intensity of the sunlight in southern hemisphere summer is about 6% stronger than the intensity of sunlight in the northern hemisphere summer at the same latitude. But that varies with these cycles. So now we can look at the combination of all of those cycles. The wobbles in the Earth's axis, the eccentricity of the Earth's orbit, and the date, and they lead to these combined changes in the amount of sunlight that's received in the northern hemisphere in the summer season. And the reason we're interested in how much sunlight is received in the summer season is this seems to have the best relationship with the changes in the amount of ice. And if we look at this series of graphs down here, we see that about every 100,000 years there's a major increase in the amount of ice. And this is a reversed scale, so that the amount of ice increases as we go downwards, and these are the intervening interglacial periods, or reductions in ice. And we see that the last warm period was just over 100,000 years ago, and there was another one about 100,000 years before that, and another one about 100,000 years before that. Those are interglacial periods, and they seem to be best linked to about the 100,000 year periods associated with the changes in the eccentricity of the Earth's orbit. But the combination of these factors leads to changes in the amount of sunlight received in the northern hemisphere at high latitudes. And that's very important, because if we can get slightly less sunlight in summer, that means that the winter time ice lasts a little bit longer. There's not as much melting in spring, and that then leads to the growth or maintenance of ice from one year to the next. Then it stays around, lasts a little bit longer, through to the winter, builds up again and lasts a little bit longer. And over thousands of years, the ice can build up. This is also very important because ice reflects sunlight. Ice increases the albedo on the surface of the Earth, and so there's a feedback as the ice grows. Less sunlight is absorbed at the surface of the Earth, and that allows the reinforcement of the cooler temperatures and the lower sunlight associated with the Milankovic cycles. So we have the Milankovic cycles initiating these changes, and then the reductions in snow and ice then leading to a reinforcement of the changes. So this is called an ice albedo, or ice feedback, that enhances the cooling, and as the ice then melts, as more sunlight returns in summer, enhances the warming. There are other natural cycles on long time periods that can also influence the long-term changes in climate. And one of the other long-term cycles is cycles in the intensity of sunlight from the sun. There are periodic variations, typically with around 11 years in the number of sunspots that are found on the surface of the sun. And you can see here a picture of sunspots on the surface of the sun. And people have been monitoring the number of sunspots on the surface of the sun for many hundreds of years, and they have long-term variations. It turns out that the magnitude of the changes in the intensity of the sunlight associated with one of these 11-year solar cycles between the peak and the minimum is very, very small. It's less than 0.1% variation in the peak-to-peak intensity of the amount of sunlight, or only about 1 watt per square meter or less change in the intensity of the sunlight in the sun. But there are variations. They do have an impact on the surface climate. Currently, we've just been going through a solar minimum, and there aren't many sunspots. But actually these longer-term variations in the sunspots seem to be associated with longer-term climate variations. And when we look at these variations in sunspot numbers over time, you can see clearly the 11-year sunspot cycle. If anything, in this most recent period here, we seem to have a decrease in the number of sunspots, which doesn't seem to fit well with changes in temperatures that have been observed over the last 20 or 30 years. But there was a period in the middle of the 17th century, in the 1600s, when there were very, very few sunspots observed at all. And this seems to be linked with a period of colder climates in the northern hemisphere called the Maunder minimum. And so there probably was a slight reduction in the intensity of the sunlight then, as well as possibly increases in the number of volcanic eruptions. And that was associated with a very cold period, when temperatures in the northern hemisphere were probably around 1 to 1.5 degrees colder than much of the 20th century. This cooling led to increase in snow cover and increase in glacial extent in much of the northern hemisphere. It led to reductions in harvest and much colder temperatures. And in fact, much colder temperatures so that there were actually a series of paintings in the 16 and 1700s that became very famous, paintings by Bruegels, showing that there really was increases in ice cover, as well as freezing in the Thames River in London, much more frequent in that period in what's called the Little Ice Age, or medieval climate anomalies, an earlier period with warmer temperatures. We can see in here as well that there was a period of relatively warmer. And we'll look later on at how those temperatures in the early, 1,000 years ago and in 500 years ago, how those temperatures compared with present-day temperatures in a later lecture. So, the Milankovic cycles are changes in the Earth's orbit around the Sun. They are affected by variations in 3 different components of the orbit: the ellipticity or eccentricity of the Earth's orbit, the changing tilt, and the date at which the Earth is closest to the Sun. Those are natural periodic variations, and it seems that the changes in the eccentricity, with a period of around 100,000 years or so, is the best explanation of the periodic variations associated with glacial and interglacial periods. But it's important to understand that these orbital changes don't lead to any change in the annual average snow cover, and therefore we need feedbacks. We're going to talk about some of these feedback processes that are really important in amplifying the role of changes in sunlight or changes in other factors. There are important amplifying processes in the climate system, in addition to the changes in the amount of sunlight due to the orbital variations. So now we're going to talk a little bit in the next lecture about a range of other long-term factors that are influencing carbon cycle and concentrations of greenhouse gases in the atmosphere.